if you think about what we know about electrostatics, our typical model of the atom shouldn't exist. You've got all these positive charges that are right near each other, and of course they're going to put repulsive forces on each other. So the fact that the nucleus is stable and holds together at all means there must be inward forces happening between all the nuclions that hold the whole thing together. An atom is in kind of a cosmic tug of war with itself. You have some forces that want to hold it together. So that really puts nuclei into three categories. In a stable atom, the inward forces always win. So that means they're always going to be stronger, and there's never a chance that the atom is going to explode. In a non-existent nuclei, the outward forces would overwhelm any inward force, so the nucleus can't even exist. So what you're left with is kind of this in-between category. And those are what we call radioactive atoms. And in a radioactive atom, there's a chance, either way, that the atom is going to remain or explode at any given moment. So when we're talking about radioactivity, we're talking about probabilities. How likely is it at any given instant that a particular nucleus is going to explode? So probability, when you're talking about atoms, is a tricky thing for people to conceive of at first, because we're talking about so many, many atoms. Trillions of trillions of trillions of them. I have a coin here, and if we talk about a chance, let's say if this coin is heads, the nucleus explodes. If it's tails, the nucleus doesn't. Every time I flip it, that's tails, so the nucleus still exists. That's tails, so it still exists. Uh-oh, lost it. Tails, so it still exists. All right, this atom's a survivor. I'm starting to think we have a loaded atom here. But the point is, when I started this, I had no idea how long this particular atom was going to last. And every time I do it, there's actually a 50% chance it explodes. So that's head. So that atom's gone. If I did this experiment again, it may not last that many times. If I did it again, it may last more than that. Every time I flipped the coin, there was a 50% chance that the atom was going to explode. That's true when you're dealing with trillions of atoms at once as well. So even though we can never predict how one atom is going to behave, any one atom could go instantly, any one atom could last for billions and billions of years. So we can't think that we're looking at individual atoms. We're looking at massive numbers of them. If we do that, what we notice is that we can describe a curve that has the population of remaining atoms. And at 50%, which is like right here, the time it takes there, we give a special name. We call this the half-life. And this is when half of the original atoms should have decayed and half should remain. After another half-life, we'll be at 25%. So that would be 2 half-lives. So half-life is a useful way of helping understand how long a particular radioactive sample is going to stick around.
The important thing to remember about this is that this is looking at the entire sample of atoms, which can be trillions of trillions and trillions of trillions of them. And it depends on the probability of any given atom in a time period decaying. So because we're talking about probabilities, it matters how likely it is for an atom to explode. When I used the coin, it was a 50-50 chance each time period. In order to see how different atoms could have different decay curves, we're going to look at some other things, namely 6-sided and 20-sided dice, and we're going to see how their decay curves look different as they have a different probability of decaying during each period. I've got a set of 20-sided dice here. I've got 50 of them. I've got a set of 6-sided dice here. I've got 200 of them. And what we're going to do is we're going to put them in a box. We're going to say 3 is when an atom decays. And we're going to roll these dice until there's no atoms left, until they've all decayed. And we're going to see how long that takes. And then we're going to graph the results on a spreadsheet. And we'll see if the curve gives us any sort of information. Alright, so I've got my box of atoms, and we're going to give it a shake, and I'm going to pull out any that have a 3 on it. This is all a game of chance, and that's the point. Just because an atom's radioactive doesn't mean it's going to decay at any given time. There's just a chance. Alright, so there's roll number 1. 1, 2, 3, 4. Just to be clear here, what I'm doing is kind of a painstaking process. I'm going through and picking out any die that happened to have rolled a 3. So we'll have said that that was an atom that decayed, that was an atom that decayed, that was an atom that decayed. So I'm doing this turn after turn after turn. And what this represents is probability. The 5 out of 6 sides that are not a 3 represent the chance that this atom doesn't decay in any given turn. The 1 out of 6 chance that is a 3 represents the probability that it does. So I'm going through and hunting for all the 3s. I'll pull them out, and then I'll shake again. And I'm just going to keep repeating the process and recording the number of remaining atoms or dice until we lose them all. I'm down to 25 dice, which means we divided by half once to get 100. We divided by half a second time to get 50. We divided by half a third time to get 25. So we would say that 3 half-lives of this atom have passed. So we're only left with 25 of the original 200. Now it's important to understand there's nothing special about these 25 dice. They were exactly the same as all the other ones. They had the same chances during the past 3 half-lives of breaking apart as any other atom. When I roll them again, some of them are going to break up, some of them are not going to break up. And we have no ideas which ones. There's nothing different about the ones that will and won't. It's just chance. It almost seems crazy as you get towards the end how long it takes to get rid of the last couple of dice. I'm going on quite a bit of time in the single numbers. But what's the chance that either one of these dice is going to decay in the next turn? Each of them still has a chance of 1/6. So this could take a long time. So this is the graph for the 6-sided dice. And we could see a couple things from it. First, I started with 200 atoms. And after 5 turns, I had to decrease to about 100. So if we're using the concept of half-life, that suggests that I have a half-life of 5 turns. Let's see if that holds up as we go forward in time. 10 turns would be 2 half-lives, so I should have half of half, or I should have 50. And I'm pretty close. Again, 200 atoms is not really realistic. It's really, trillions and trillions. So the fact I'm pretty close is what I'd expect. So 3 half-lives is 15 turns, so I'd expect to have around 25, and that is what I seem to have. 4 half-lives would be 20 turns. I expect to have around 12.5, which I do. So you should be able to look at one of these graphs and determine a half-life from it. And what I want to do now is I want to look at something that has less probability to decay during each turn, namely the 20-sided die. And I want to see how that curve is different. Let's take a look. These dice have a much lower probability each turn of decaying, so we can have many turns where none decay at all. So this curve, I want you to predict how it might look different than that for the 6-sided dice. On it. This is the 20-sided dice, and there are 50 of them to begin with. In that first turn, there weren't any that rolled a 3. There's a much lower probability that any individual die is going to land on a 3 when we're talking about this situation. Let's see if we can find any that have decayed this turn. Oh, there's one. And I guess that's it. So here's the graph for the 20-sided dice. And you can see we started with 50. This curve's not as smooth because we had significantly fewer dice, just because I didn't have as many 20-sided dice. But we can see that the shape is pretty similar. If we started with 50, one half-life will be when we get to 25. And that seems to have occurred around 20 turns. Note that this is significantly longer than what we saw for the 6-sided dice, because there is much more probability in this case that the dice won't decay in any given turn. There's 19 out of 20 is a higher probability than 5 out of 6. So half-life is sort of a measure of the probability of having a decay, how likely an atom is to decay. The less likely, the longer half-life you're going to have. So the fact that every radioactive isotope has its own half-life, which is based on the probability of the atom decaying in a time period, that's really important for understanding a couple of scientific ideas. The first of them is called radiocarbon dating, and I'm sure you've heard of it. It lets us determine how long ago a plant or an animal died. Basically, in the upper atmosphere, an isotope of carbon, carbon-14, is continually created. And as long as a plant or animal is alive, it's exchanging atmospheric gases. It's going to have a pretty constant supply of that. As soon as it dies, radioactive decay starts to get rid of its carbon-14. So by looking at the ratio of carbon-14 to its daughter nuclei, you can sort of figure out how long something's been dead for. So this is my wife, Dr. Elsbeth Dowd, and she's an archaeologist. She's working on a Caddo Indian village in McCurtain County, Oklahoma here. And my understanding is that the date they got on this village was very specific. Something like 1348 AD plus or minus 10 years. How do you do that? Radiocarbon dating. Basically, they found part of a house that had been at this site, and the tree that it was made out of had lived at that time. So this is how archaeologists determine dates, paleontologists determine dates this way, even geologists going back into Earth's distant geological history. Carbon dating only gets you back a certain amount of time, but there are other isotopes that can get you back much, much farther in Earth's history. So that's one place for half-life. We use it as kind of a clock to figure out when something was created. Half-life is also really important for understanding how long something will be a radiological hazard. And I'll give you an example of this. In the United States, we have a really big problem with nuclear waste. All sorts of power plants were built across the country in the 1960s and 1970s with a promise from the U.S. Department of Energy to deal with the waste, to put it in a safe place. And that hasn't happened, and we've really got to figure that problem out, because it's estimated that that waste will continue to be a hazard for tens of thousands of years. We know that because the half-lives of these materials are super duper long. And for the radiation to decrease any appreciable level, you have to go several half-lives. So if something's a hazard now, and its half-life is thousands of years, it's going to be many thousands of years before you get any sort of improvement in its safety. So in order to understand how long we have to plan for the radiation safety, it's important to understand the idea of half-life. This is a mountain in Nevada called Yucca Mountain, and it's currently the U.S. government's position that that's where our country's nuclear waste is going to go. This has been very caught up in politics, and a lot of people have fought back and forth over this. So it's unclear at this time where that nuclear waste is actually going to go.